So now we're going to look at how we can run the standard normal distribution computations using the normal CDF function in the calculator, where there's a little bit of variation here depending on the type of calculator you're running, but hopefully we're going to be able to see what we need regardless. So first thing you can understand here is with all these problems, you technically can just do everything using the table where you go to the singles digit and the tenth, then scroll over to the appropriate amount of hundredths in the appropriate column. And this does work, but for one, I don't think it's a very efficient way to do things, and two, it makes a explicitly continuous thing into a explicitly discrete construction, which I disagree with philosophically, besides not being, in my opinion, a particularly useful approach. But anyway, if you want to see this in the calculator, what you would do is go back into the distributions, like in chapter 4, so second vars for distributions, and we're going to pick normal CDF here, where remember, CDFs are what we use for any type of accumulation, whereas PDFs are what we want for any single point. But here, we're talking about a continuous thing, so the PDF would tell us something about a single value when there's uncountably many of them, and therefore isn't very useful for what we're trying to do here. So generally, we're going to use CDF instead. In this case, we'll pick normal CDF, and we have these inputs here, the lower boundary, upper boundary, mean, and standard deviation, where it defaults to having a lower boundary of -1 E99, which is to say a -1 followed by 99 zeros, and a possibly large negative number to say we're going to go off as far as we possibly need to in that tail, and then a little bit farther still, just to be sure. You can make that -10,000 though if you want to. It doesn't make that much of a difference, at least for this type of problem. Then the upper boundary is how high we're going to go, where in this case we're going up to 1.15. So the calculator is defaulting to working with accumulations up to a point. It's defaulting to working with CDFs as they're kind of designed, but we can adjust that if we need to go above, which we'll see later. And then from there, because we want the standard normal, we want mean mu equals 0 and standard deviation sigma equals 1. So again, calculator defaults to that, and we'll make it run, where we get the desired decimal up to 4 decimal places of specificity. And if you don't have these menu options, so I'll turn off the wizards just for now so you can see what that looks like. When you go into your distributions, normal CDF, it just pops up like this. Just put in a large negative number if you want. -10,000 generally gets the job done. But you put in your lower boundary, comma, upper boundary, comma, 0, and 1. And then you close all that off, get essentially the same value. Again, for this problem, the difference is so many decimals down the line that it really doesn't matter. For a second example, we're going to do essentially the same thing, but different number, and I'm going to go back to using the wizards just because that's what I'm assuming most of you are going to be able to do, and also because it's a little bit cleaner. So, if you want to find the area corresponding to a score of -0.24, go to normal CDF using second vars for distributions. We have the same lower boundary. Our upper boundary now is -0.24, and we're still working with the standard normal distribution here, so mean mu is 0, sigma is 1, run it, and we get the desired probability of about 40.52%, rounding to 4 decimal places. On the other hand, if we want to find the area between two z-scores, it's not actually that different. So first, second vars for distributions, normal CDF, where now our lower boundary is not some stand-in for the largest negative value we can come up with. It is specifically -1.5, and our upper boundary here is 1.25. Put those numbers in, and you make it run. So you get a value of about 0.8276 here. So notice, in that fourth decimal place, you've got a little bit of a rounding error, because if you use the normal distribution table, it's a little bit more subtle to get those numbers. So you're off by a very small amount. This is something that's going to happen a bit more in this section in particular, and going forward actually, that I really find frustrating because the book insists on using the tables when I really disagree with that. Just understand that it will happen. Usually your answer is going to be close enough, though, that MyLab will still take it.